Hello class, this is our lecture on variability. In previous lectures we've talked about central tendency, the statistics of the mean, median, and mode, which deal with the center of a distribution. But we also need to know about the dispersion or the variability of the data points, basically how spread around a given center all the different measurements in a data set are. For the most part, as I said before, we will be focusing on the mean. That's the average or the mathematical center point of a distribution. And then when we talk about an individual score and how far away it is from the mean, we're talking about a deviation. So a deviation, as you can see here, is the distance separating a given score from the mean. So a deviation is the distance separating a score from the mean, and we can look in our samples here. Here's A, we have a mean of 6, and it's comprised of these scores, 0, 2, 6, 10, and 12. So if our mean for the sample is right here, here's our mean of M, a score of 2, this score here, has a deviation equal to 4. So this is 4 away from the mean. Just as a score of 10 is also 4 away from 6. So this score, this x value here, has a deviation of 4. We can look at our second sample here in B, which also, sample B also has a mean of 6. But these scores are a little bit more tightly distributed. We have 4, 5, 6, and 7. 4, 5, 6, 7, and 8. Right? And when we look at the deviations here, the deviations for each of these individual scores is smaller than they were in the previous samples. So for a score of 4, we have a deviation of 2. For a score of 5, we have a deviation of 1. And then we have 1 and 2 again here on the other side. And now finally we have sample C. This would be a uniform distribution where all the points are the same. And this has no deviations for any of these scores, since 6 minus 6 for any of these is going to give us a deviation of 0. So this is one way of characterizing different distributions, or beginning to think about how we would characterize these distributions, where this first one has relatively high deviation amongst the scores, this one being medium or a moderate form of deviation amongst these individual scores, and this one has no deviation amongst the scores. So when we're measuring variability, we are measuring the dispersion or spread of data in a distribution. So a deviation is the measure of one score's distance from the mean, and variability is an overall measure of all of those scores' distances from that mean. Variability is always going to range from 0 to a positive infinite value. It's never going to be lower than 0. So just as you saw in our previous slide here, I called all of these as positive values. So 4, 4, 2, 1, and 1 and 2, right? None of these are considered -1 or -2. All we care about is the absolute distance of a given score from the mean. Variability is never going to be negative. As long as there's a difference, there is some amount of variability. Our measures of variability that we're talking about today are going to be range, variance, and standard deviation. The range is the difference between the largest value in a data set and the smallest value in a data set. It can be calculated as the maximum value minus the minimum value. This calculation only considers the largest and smallest values of a distribution, so it's a fairly simple way to understand the dispersion of scores. And it can be informative as long as you don't have really large outliers, meaning really extreme points within a distribution. Below we can see ways that we would find the range for a given set of scores. So for this range here, Our largest value is 5, our smallest value is 1, so 5 minus 1 gives us a value of 4. And then for this, this distribution of scores here, we have 100 as our largest value and 2 as our smallest value. So 100 minus 2 gives us a range of 98. All right, so for this given example with the data set, we are going to compute the range. So we're going to identify the largest value and subtract the smallest value. The largest value here is 15, and the smallest value is 10. So we simply subtract one from the other, and we get 5 as the range for this data set. So a very straightforward computation figuring out the range. So continuing onto variance and standard deviation, the variance and standard deviation are indicating how much the scores are spread out around the mean, right? The range doesn't have anything to do with the mean, it's just the largest and smallest value, whereas the variance and standard deviation are going to be calculated by subtracting individual scores from the mean and then doing a couple other computations on them. We've actually already calculated sample variance before in one of our first activities when we were working on statistical notation and computations. So variance is a measure of variability for the average squared distance that scores deviate from their mean. So just like when we looked at a deviation before, it's taking that deviation and squaring it and then dividing all of those squared distances that you've summed up by the number of scores in that sample. Just like with a deviation, the value can be 0, but it can't be negative. It has to be 0 or greater, because once you have a difference between scores, there's some amount of variability, therefore you will have some amount of variance within that data set. So it can go from 0 to positive infinity. Variance, unlike the range, is a preferred measure of variability because all of the scores, all of those data points inside of a data set are included in its calculation, as opposed to maybe just using the maximum and minimum values to understanding spread of data. So for the population variance, we are calculating the true or actual variance of the population of scores, and we can see the equation for this here. This equation is using this mu symbol, right, which is our symbol for the population mean, and it's also using n, the total n or total number that's being measured here. Looking through this equation, we can see that we have a sigma, meaning to sum, and we have x. This x would stand in for each one of the scores within your data set or within this population. And so it's x minus the mean, which is a deviation. Remember, the difference between a score and the mean is a deviation. We square that value. That way, any negative deviations that we get here are turned into positive values. We sum all of those up, and then we divide by n. So as an example here, let's say we have a score of 4 and a mean of 6. We're going to find the difference between these two, which is negative 2. And we can also, at the same time, check out a score of 8 minus 6, and this gives us a score of positive 2. So those are deviations of 2 scores. We square these, both of which are going to turn into 4. And then this gives us 2 scores that we are then going to sum up. 4 plus 4 is 8. We're dividing by n. In this case, I've only looked at 2 scores, x1 and x2. So we get 8 over 2, giving us a variance, at least in this little toy example here, of 4. So that's an example of a very simple variance calculation. Now, if you looked at the standard deviation equation, you'll see that they differ only in one respect, which is that the standard deviation has a square root over it. So by squaring this variance here, we get a standard deviation equal to 2. So pretty straightforward calculations, nothing more complex than what we've done so far in class. And you can also note here that this is the symbol for the population standard deviation. So now, as we move on to sample variance, we're going to see that the equation changes a little bit. This is an equation that we've done before. There's two specific things to highlight. The first is that we are no longer using n in the denominator of this equation. We're doing n minus 1 because we're working with a sample. This is referred to as a degrees of freedom control, and it's something that we'll address a little bit later in the lecture here. We are also, in this computational formula, using the sum of x values squared, and then the sum of x's squared, right, divided by n, and then divided by this n by 1 to come up with this equation. So this is what we did in our activity on notation and computation. So as an example here, let's use those scores that were referred to before in this computational formula, and I'll draw them in over here. So let's say we had a score of 4 and a score of 8. These are going to be squared and then summed together. So we get 16 and 64. Added together, it gives us 80 over on this side of the equation, right? That is our sum. This is going to be subtracted from these over here. So we have the sum of x's then squared. 4 plus 8, that's summing them together, is 12. And 12 squared is 144. I'm just going to write that out here instead of doing it in the long form. We divide this value, division goes before this subtraction, by n. So that's going to give us a value of 72. And 80 minus 72 gives us a value of 8, so that's going to be the overall numerator of this equation. Right? This simplifies to 8 over n minus 1. I only considered 2 scores here, so that's going to be over 1, which divided by 1 is itself. So our sample variance in this little toy example here, this is the sample variance symbol, is 8. Right? Here's our sample variance symbol here. So now, while calculating this example variance from that sample data set, we can fill out these charts, and we've been practicing this over the last few activities. I'll just fill out the top row here before clicking on to the next slide. So 10 times 1, that's f times x, right? Gives us 10. 10 squared is going to give us 100. And then the frequency f times x squared, so that's 1 times 100, right? It's these columns being multiplied, also gives us 100 here. So that's basically the operations that we're going through. It's the values, these first two multiplied, and then the second and fourth columns multiplied, giving us the value here in column 5. This is what our filled out chart looks like, and I will highlight the important parts. So we've done our frequency count here, and we've seen that n is equal to 18. That's our total number in this sample. We have our sum of x's, which is 246, and we have our sum of x's squared, 3,406. We plug these into the equation here, so we can see that n is going to go right here. Sum of x is going to go right up here, and I'll highlight this in a different color. So sum of x is filled into here, 246 up top, and then sum of x's squared goes over here, 3,406. So we can see right where those plug in to this formula. We do our computation, and we end up getting a sample variance of 2.59 from all of these values here. Now, moving on to the standard deviation. The standard deviation indicates the average deviation or average distance score that a score deviates from the mean. So it's as if we're taking all those deviations from those individual scores and calculating a mean of those deviations. This is a measure of consistency. It's really telling you how spread scores are around that mean. And as we've seen before, it's simply calculated by taking the square root of the variance. Now, the standard deviation is one of the most used statistics when talking about data sets, talking about their distribution, and talking about maybe how close they adhere to normality. The larger the value of a standard deviation, that means the more scores are going to be spread out around a mean, therefore the wider the distribution is going to be. If you imagine that bell curve that we've seen before, a standard deviation that's really large is going to be a very, very pronounced bell shape. It would look almost more like an arch potentially than a bell. A standard deviation that is really small is going to be a really, really tight bell shape. So, as we've seen before, the standard deviation formula is the same thing as sample variance, just with a square root put over that whole computational formula. So, going back to our example from the variance that we've just calculated, we went through and calculated a variance of 2.59 to turn that into a standard deviation. We take the square root of this and we get a standard deviation of 1.61. Very straightforward. So now that we are developing our understanding of sample variance and population variance, we should talk again about the differences between working with a sample and a population. Here's a quick example. Imagine that we have the average, the GPA measurements of every freshman at UC. We would consider that a population, those are population measurements. Because we have access to all of those scores, we would work with this equation that we see up here in the top, and we could use that as a way of calculating the variance among those GPA scores. Now imagine that instead of having access to all of those, we were measuring maybe only 50 freshmen and what their GPAs are. So that would be a sample of that overall population. And now whenever we're using a sample, there's a possibility of measurement error, of some sort of difference between that sample and the overall population. The degrees of freedom, which I mentioned before, corrects for this kind of measurement error for the fact that sample variance tends to, or always underestimates the population variance. It's a biased estimate. And all that a degrees of freedom operation is subtracting 1 from the number n within your sample. So when we have this big N here, this would be our overall population size, how many measurements we took. So let's say it's something like 5,000 for freshmen at UC. And then in our sample example that we gave here, we have this little n, and I said that we would have 50 scores, so a degrees of freedom calculation is simply 50 minus 1. So our degrees of freedom, listed as df, is 49. We can see in this equation here that when we're calculating sample variance and we use degrees of freedom of n minus 1, this is the definitional formula and the computational formula, that when we're using that, we essentially get a more conservative estimate of the sample variance, as opposed to using that one of the overall population. So now let's build our conceptual understanding of standard deviations and normal distributions. So for a normal distribution with any mean and any variance, there are empirical statements that we can make about the relationship of the standard deviation and the percent of scores that fall around the mean. Remember, the standard deviation is how far and how spread scores are around the mean. This first estimate is that, or this first empirical statement, is that at least 68% of all scores lie within one standard deviation of the mean. And I'm going to highlight that over here. So that means below the mean and above the mean by one standard deviation. In this case, the standard deviation is 4. So 4 above 12 and 4 below 12, we're going to find 68% of the scores. 95% of all scores lie within 2 standard deviations of the mean. So that's this area here plus the yellow area. And I'll generally cover that over. So this is going to comprise 95% of the scores. And then finally, 99.7% of all scores lie within 3 standard deviations of the mean. So that's essentially all of this area here underneath our normal curve. So now that we have this general understanding of how the standard deviation and a normal distribution are related, this gives us an idea of how it might be useful to have a measure of standard deviation when we're talking about a data set. If we have a really large standard deviation, we would know that the scores spread quite a great deal away from the mean. But even though those scores are spreading a great deal from the mean, this percentage relationship is still going to remain true. There still would be 68% within one standard deviation, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. Now let's review some general characteristics of standard deviations and keep this idea of the normal curve or the bell curve in mind when you're thinking about what these characteristics mean. So first of all, just like the variance or the variability, standard deviation is always going to be positive. Whenever there's variability, there's going to be a positive value, meaning some difference between scores. Negative variability doesn't mean anything. The standard deviation is used to describe quantitative variables, right? Because it's a numeric value and it's used to describe variables in numeric units, it wouldn't make sense to try and calculate a standard deviation of categorical or nominal data, something that is closer to qualitative data. As I used my terrible example before, you can't have something between a freshman and a sophomore. Froshmore isn't a word, right? And finally, the standard deviation is most informative when it's reported with the mean. And this is just good statistical convention as well as APA format. Whenever you report a mean, you're also going to report the standard deviation. This is just a good way to inform a reader or someone you're communicating results to a understanding of both the central tendency of the data and the spread of the data. So really, these two numbers together can give someone a good description of a kind of data set, of any example data set that you're working with. We've talked before about how in descriptive statistics, what we're really trying to do is simplify our understanding of some kind of measurement of some data set down to 1 or 2 numbers so we can quickly understand what's going on within the data. So if someone gives you a mean age and then a standard deviation, they're essentially telling you a whole lot about that data set. let's say, for example, in the previous example of the freshmen and their GPAs, we have a mean GPA of 3, and then we have a standard deviation of 0.45. So essentially, that is telling us that while the center of that distribution is somewhere around 3, if we go up 1 or 2 standard deviations, that there are going to be students whose GPAs are going to be somewhere, one standard deviation up would be around 3.45, and then 2 standard deviations up would be 3.9, right? So basically, 90, going back to our assumption about that normal curve, 95% of that data is going to fall within that range. So someone can kind of immediately calculate and understand a little bit about where the percentages of a given distribution lie. And continuing, the value for the standard deviation is affected by the value of every score in the distribution. So in our previous lecture, we talked about how adding outlier values would shift the mean. The same sort of thing would happen to the standard deviation because it's calculated using every single score within a data set. So adding or subtracting a constant to a score isn't going to change the value of the standard deviation, just like it wouldn't for the mean. Multiplying or dividing each score using a constant is also going to change the standard deviation correspondingly. So if I added 5 to every score, the standard deviation is not going to change, right? Because the differences between those scores and the mean isn't changing at all. But multiplying and dividing each of those scores by a constant is going to change the standard deviation by that constant as well. And then one final characteristic here is that for any roughly normal distribution, the standard deviation should be equal to about 1/6 of the range. And that's just going back to this idea about the bell curve, so a sort of adequately normal distribution, the standard deviation is going to cover a certain range of that data set. And if you're finding standard deviations in any of your measurements that aren't particularly close to 1/6 of the range or aren't close to what you'd expect, then you may not be dealing with a normal distribution. So just referring back once more to this picture here, one standard deviation, right? If we divide this up into 1, 2, 3, 4, 5, 6 separations here of this distribution, we can see that a standard deviation essentially comprises 1/6 of the range of these possible scores here. All right, and I hope this recorded lecture has been helpful. If you have any questions, you can email them to me and I can potentially post a video response or maybe just put together a document regarding questions that I've received from the class and then distribute that out to everyone along with my explanations so we can all have a good understanding of standard deviations and normal distributions as well as how we can calculate variance. These are going to be important concepts as we move forward through the course and in general to your understanding of how descriptive statistics are calculated.